they would. So, as I'm sure you all know, I think it's general interest of mathematics is homotopy theory in general, but then specifically also higher category theory. For example, complete serial spaces are one of his inventions. And then, as we will find out in this series of lectures, Charles is also interested in elliptic cohomology theories a lot and in power operations. I expect those will play a role in the talks. Okay, so this is maybe what I've prepared about our speaker. As you also know, this is not just an individual lecture, so it's a 90-minute lecture today. We'll have a short break, roughly in the middle, so 10-minute break in the middle, so we can all breathe some air. And there will be 5 more lectures, always Monday, Wednesday, from 10:15 to 12. The first 4 lectures will be here, like today, and then the last 2 lectures will be part of the workshop at the Max Planck Institute. Now, without much further ado, I hand over to Charles.
All right, thank you. Hopefully I'm audible and can be seen. I'm going to close this a little bit. Thank you for giving me the opportunity to give these lectures. It's quite an honor and a little bit intimidating. Today I want to start, the first talk is going to have the character of an introduction or an overview. I want to sort of introduce the basic objects that I'm interested in and sort of the general themes. There won't be much, therefore, meat in this talk. There will be more in the later talks, but that's sort of the way it works out. All right, so let me start by giving sort of a pseudo-historical account of elliptic cohomology, just very roughly, just to sort of get some context. So I guess this started by thinking about genera. So I'm going to describe this as though nobody knows this, although probably everybody in the room knows what I'm going to tell you next. So there's this notion of a genus, which associates to a closed manifold of some type, some kind of invariant in a commutative ring. And the idea is that this function has nice properties. For instance, it's additive and multiplicative. So there's a product of manifolds that goes to the product. And also that it's a Bordism invariant. So if I apply this to a manifold which is a boundary of a closed manifold of the same type, a boundary of a manifold with boundary, then that should give me 0. And as probably everybody knows, you can interpret such a function as a function on a ring, namely the Bordism ring. So this is equal to a homomorphism from a Bordism ring. So for instance, if I'm interested in orientable manifolds, I'll have a ring homomorphism from the Bordism ring, MSO, into R. Or maybe I'm interested in stably almost complex manifolds. In this case, I have a homomorphism from MU star into R. All right. So there's a formalism for constructing genera that take values in a ring that contains the rationals. This is due to Hirzebruch. And the observation is that genera of this type can always be constructed and calculated entirely using characteristic classes. So, for instance, let's take a MU star genus, just for specificity. Let's suppose that this ring contains the rationals. Associated to this is a characteristic class. So I'll call K sub phi. And this takes an appropriate kind of vector bundle over an arbitrary space, in this case a complex vector bundle, and gives me an element in the cohomology of that space with coefficients in this ring R. And such a characteristic class is completely determined by its characteristic series. I can't spell. Well, that's what you get if you take this class and you evaluate it on the universal line bundle, which lives over BU1. So the cohomology of BU1 is a power series ring over R. And so we might write this just as a function of this power series. Okay. And so there's a way to reconstruct the characteristic class from the characteristic function using the Whitney sum formula and the splitting principle. So roughly speaking, you handle the case of sums of line bundles, and then you pass to the general case. And then there's the formula for the genus is evaluating this characteristic class on the tangent bundle and then pairing with the fundamental class of the manifold. Sure. So this is sort of the formalism. I've only introduced it so I can talk about these characteristic functions. If I want to do MSO, the same formalism applies, only in this case, my characteristic series is invariant under inversion. You get a similar theory. And I haven't told the whole story. This is really something you can calculate from the usual Chern classes, and this you can calculate from the usual Pontryagin classes, as probably everybody knows. So what's the right procedure for erasing? Should I wash the board every time?
That's the traditional German way.
Well, I know it's a traditional German way.
Also just do the
Let's see how wiping works, and then maybe I'll...
Oh, yeah, you have one more board.
Oh, there is. Oh, okay. Awesome. Let's
Then
leave that
the
up.
question comes on.
Okay. That gives me more time. Excellent. Sure, why not? So this is meant to be a little bit rough, so I didn't even put the star in on R. But of course, you usually take that to be a graded ring. But in some examples, I don't need to take it to be graded. So for instance, let's do some examples. So let's be agnostic about whether it's graded for these purposes. There's the Todd genus. So this has a characteristic series. I don't think people can see this. What is this? K Todd of x is x over 1 minus e to the minus x. And that's a power series over z. Over Q. And on stably almost complex manifolds, this gives the genus. And although a priori you might think that this is a rational number, it's in fact an integer. So there's a reason for that. The reason is that there's a geometric or analytic origin for this. So in this case, this turns out to be some Euler characteristic. So this is if, in particular, the particular interpretation here I'm giving is if M is actually a complex analytic manifold. It's the Euler characteristic of coherent homology of M. I think I have that right. All right. And then another example, of course, is the A hat genus. K A hat x is the series, it's a characteristic series, x over 2 over hyperbolic sine of the same. And on spin manifolds, this also gives an integer. Even though a priori you might expect a rational number, and this is because it's the index of the Dirac operator on M, on the spinor bundle. All right, so the interest in these genera is not because you can define general genera on this cobordism ring, but rather that there are some very special examples that somehow arise naturally from some geometric situation. And so this was always the motivation for this. These genera come in families versions. Families, genera. So, so in the cases in question here, we might have not just a single manifold, but some family of manifolds. M over S. So for every point in some space X, some parameter space, we have a manifold. And so each manifold in each fiber has a genus, but the observation is that we can expect these genera to fit together not merely into some function, into some ring parameters by C, but rather into a cohomology class. So the family's genus associates to a suitable bundle of manifolds some kind of cohomology class in some cohomology theory. E is some generalized cohomology theory. So I may think of this as a family's version of a genus taking value in E star of S. So in these classical cases, we know what the theories are. Their versions of Ktheory are the ones that receive a family genus. So for instance, the A hat genus, the family of spin manifolds, takes values in KO. This is if n here is the dimension of the fibers. I think it's right, KO minus n. Oh, sorry, it's of S, exactly. Right. And if you just have a single manifold, then you have KO of a point, and that recovers the usual A hat genus, at least if the dimension of the manifold is a multiple of 4. Because that's when KO of a point is an integer, is the integers. So this is sort of a geometric picture, and it's sort of one of the things that comes out of the index theorem. It also has a homotopy theoretic description. So in homotopy theory, or topology, we describe this by saying we have a natural transformation of cohomology theories. So we have some kind of cohomology theory that's a Bordism theory. And then we have some other cohomology theory. So this picture for the A hat genus would be KO. And we have a transformation of cohomology theories. And this should be a map of multiplicative cohomology theories. Or if we like to think about representing objects for these things, we observe that our multiplicative cohomology theories are represented by commutative ring spectra, and this should be a map of commutative ring spectra. So producing such a map actually automatically constructs a genus and even a family's genus. And we can interpret these constructions that come from index formulas as actually producing, passing through this construction of a map between cohomology. Okay, so that's sort of the background. Now, let's say briefly what the elliptic genus is. So to talk about the elliptic genus, I have to say what modular forms are. Now I have to do some erasing. Let's see. Let's do this. I'll make this too wet. Let's see how this works. Do I have a squeegee? Or?
It's on the other side. You're holding it up.
Oh, cool. This isn't wet enough. Oh, well. So to describe elliptic cohomology, I better start by describing modular forms. So, we set up modular forms. So, modular forms are sections of line bundles over the moduli of elliptic curves. So, let me do this in the complex analytic case. It's relatively easy to describe. So, I'm going to write X. This will be the double half plane. subset of the complex numbers. Over this X, there's a bundle whose fibers are tori. So the fiber over tau is going to be the complex numbers divided by the lattice generated by 1 and tau. So we get this bundle. This bundle has an action by a group which is GL2Z. It's an equivariant bundle in the category of complex analytic manifolds. Here's the action. So if I have a matrix in here, then A acts on X by fractional linear transformations. A acts on the fibers in the following way. So let's take a typical point T and then the equivalence class of some Z, the complex numbers. So that's A tau, and then I have a transformation, which is basically multiplying some number by Z by some number. Here it is. If you look at what this does on fibers is associates to every A and every tau an isomorphism of elliptic curves. So this fiber, of course, is a complex analytic elliptic curve. It's a genus 1 surface. It even has a marked point because the origin is can be picked out there. So this thing gives me a function from the fiber at tau to the fiber at A tau. And it's an isomorphism. So putting this all together, we get some kind of orbifold. So I have this map, and it has equivariant with respect to this action. So I'll take some formal quotient, and I'll think of that as a orbifold or a map between orbifolds. And this is the universal example of a complex analytic elliptic curve. So this is the universal family of complex analytic curves. There's a bundle over this object. So omega, which lives over X, it's also equivariant. Omega at tau can be defined as the cotangent space at the identity of the fibers. And that's a holomorphic vector bundle over chi. And then, well, what's a modular form? A modular form of weight k is, well, it's a function that's a section of this equivariant line bundle, or rather of the kth tensor power, that's the weight, which satisfies a growth condition. Let me say what that is. So the idea is that when tau approaches, let's say, positive imaginary infinity, let's write q is equal to e to the 2 pi I tau, then f as a function of q admits expansion. Complex numbers, and this is a series with only positive powers of q. And so the growth this is the growth condition. So it admits this expansion. And so the idea is this is sort of giving the behavior of f of tau as well. The imaginary part of tau becomes large. Okay. You can actually interpret this as saying that I'm going to take this orbifold, x mod gamma, and adjoin a point in infinity. In fact, I can extend it to a larger orbifold. And let me just call that x mod gamma bar. So that's sort of this thing plus a point in infinity, if you like. And then we can say exactly that a modular form is a section of an extension of our bundles, line bundles omega to the k over this guy. So that's where f lives. And this is what's called the space of modular forms of weight k. Okay, so that's a modular form. There are variants of this where we replace, for instance, gamma with, here it is, with a subgroup. All right. So the elliptic genera are genera that take values in the ring of modular forms. They were introduced first by Oceanine, and then Witten made an important contribution. I want to give a little idea of that. But, oops. All right. So, actually, I meant to give you some examples of modular forms. One family of examples is given by the Eisenstein series. So I'll call these G2KQ. I'll write their Q series. This is defined to be, let's take it to be minus B2K over 4K. That's a Bernoulli number plus a certain series of powers in Q for n greater than or equal to 1. The coefficient of Q to the n is the sum of powers of divisors of n. Right. If this is a modular form of weight 2k, if 2k is greater than or equal to 4. One can also speak of this series when 2k is equal to 2, but then it's not a modular form. If you rewrite this in terms of the tau, you can extend it to the whole double half plane, but it doesn't have the right transformation properties. It's not an equivariant section. Right. So, in fact, the extension to the upper half plane up to a scalar, this is some kind of sum over lattice points. In tau plus n, where m and n are all pairs of integers except 0, 0. That's up to a scalar. Okay. That's why they extend. And so these give elements. Actually, I should have actually put something here. I'm actually going to call this not MFK. This is MFK tensor C. These are complex analytic. Okay. So in fact, it turns out that MF star tensor C is a polynomial ring on G4 and G6. Okay. All right. Here's an important feature of this. I've described a complex analytic story, but elliptic curves are actually objects of algebraic geometry. In fact, they're even objects of arithmetic algebraic geometry. I can have an elliptic curve over any base scheme. It's a proper smooth curve of relative dimension 1. So I've described some kind of moduli space of complex analytic elliptic curves, and I even compactified that space by putting in a point at infinity. Well, you should somehow think of that as mapping to some more even richer object, which is the moduli stack of algebraic elliptic curves. I'm not going to go into detail about how you describe this thing, but there it is. The line bundles that I had over this funny orbifold actually pull back from honest algebraic line bundles. So there's an omega here. And we can actually define the ring of integral modular forms to be the global sections over this compactified moduli space of powers of the corresponding line bundle. These are algebraic sections. Okay. So in fact, this ring can be described. In fact, this was actually just the rationalization of that ring, or the complexification. This ring is the integers adjoin C4 and C6, but then I have to invert something called delta. Or sorry, I don't have to invert something called delta. I have to throw in a certain fraction of C4 and C6. C4 cubed minus C6 squared divided by 12 cubed. That quantity is called delta. So this is, if you like, a subring of this ring, where I identify C4 is really 240 times G4, and C6 is 504 times G6. So this is a subring of what I already described. Okay. How am I doing on time? Oh dear. ML is defined over spec Z. Okay. All right. So here's what happens. Let's move this up. So the Witten genus, or elliptic genera in general, in particular the Witten genus, which I'll focus on. Let's see. Witten. So the elliptic genus is a genus that takes values in rings of modular forms. So as I said, Oceanine gave the first example, but there's a related example due to Witten, so I'll describe that one. Let's see. All right. That's dry enough. So this is a Witten genus. So this is associated to the characteristic series given by the following formula. It's the exponential of a series. Huh? Is something wrong?
No, it's just about grading. You said that today
We shouldn't worry about grading today. This is a series in MF star tensor C power series variable. Okay, and there's an associated genus, which, as defined here, would take a manifold and M something and give values in fact, I could define this for MSO. And it would give values in modular forms tensor C. Okay, this expression is effectively what's something called the Weierstrass sigma function. So the Weierstrass sigma function is defined by the equation I just wrote down. It also depends on tau. And this object is the thing that defines the Witten genus. However, as defined, maybe it's not so exciting. It's just some random formula. But it has a remarkable property. Not only does it take values in modular forms, but the following happens. If my manifold M that I apply this to is spin, and a certain characteristic class vanishes, it's usually called P1 over 2, because you can define P1 on spin bundles, but you can also define a half of that. If this is also 0, then the value of this genus is not merely a complex modular form, it's integral. So it lives in MF star. Okay. So this is a fascinating fact about this construction. So we actually get, coming out of this, something that is actually an invariant in arithmetic algebraic geometry, not merely complex analytic. And there's an explanation for this. It can actually be proved by relating the Witten genus to the A hat genus. Let me not tell that story in the interest of time. But actually something even more fascinating is going on, which is Witten's explanation. So Witten observed these features, and he actually explained them as coming from conformal field theory. That was a physics explanation. So I can see here that I'm running behind on time as I expected. So since I am not an expert on conformal field theory, let me not say too much about this. I'll just say in words a few things. So probably, whether or not you know anything about field theories, you've seen much discussion about what's called topological field theory. And you've seen that something called the cobordism hypothesis, which involves thinking about a topological field theory as a functor between two n categories. So for instance, if I have a two-dimensional field theory, it's a functor between some bordism 2 category, built from pieces of two manifolds, and some other 2 category, that's some target category. And those are topological field theories. There's something that's even more sophisticated than that, which is instead of looking at just manifolds, you put some geometric structure on your manifolds. So for instance, you might have conformal structure, some kind of complex analytic structure or something, and then you have some kind of geometric field theory. And that's the sort of field theory that this comes out of. So this is a two-dimensional conformal field theory. So in particular, a conformal field theory takes some suitable category of bordisms of two-dimensional things, but probably they have to be decorated somehow by some geometry. In this case, you need some geometric structure like conformal or something like that. In this case, they also need to be supersymmetric. And probably other things have to be true that I don't even know about, but it's some kind of 2 functor to some target category. And the basic idea is that one kind of closed 2 manifold that you can plug into this is a Riemann surface. And what should come out of a closed 2 manifold is a 2-morphism in the target 2 category, which instead of the basic example will just turn out to be a complex number. And so the basic idea is, well, the very sort of stupid way, the most sort of naive way to think about what this is giving is that I could take this 2 manifold to be some kind of complex numbers modulo lattice, a torus. And then a field theory will give me a number. Well, that's what a modular form is. Something that gives you a number, or at least a section of a line bundle, associated to an elliptic curve. So if you, I guess the moral is that the Witten genus comes from a particular choice of field theory, I think that's the right way to say it, on some situations like this, but probably elaborated a great deal. And the reason that it gives you a modular form is exactly because of this fact. I can evaluate it on closed surfaces, and in particular, I can evaluate it on elliptic curves. This function is usually called a partition function in this context. Okay, so that explains why the Witten genus is a modular form, so that's good. But there's this other remarkable property, which is that I have an integrality property. And that arises from, I guess, something you might call dimensional reduction or something. I decided I couldn't really even figure out how to explain this in a useful way, so I probably shouldn't. But the idea, I guess, is that instead of thinking about closed 2 manifolds, you can think about things like this. And things like that have circle actions. And this tells you that, well, okay, let me just ignore this. I'm sorry. There's a different explanation for why this gives.
Can I add
Yep.
a word here?
Yes, do so, please.
Historical misunderstanding of Graham Segal. So this field theory is not conformal. So when you press
Okay.
it, which I did, it's only defined on flat Riemann surfaces.
So it really is Euclidean.
Just Euclidean.
Okay.
It's perfectly fine for your talk because the torus is flat.
Yes.
And the cylinder you're about to use.
So that was already in Witten's. Witten understood that already, you think?
I think you need some extra geometry on the manifold, like reaching flat.
I see.
Or some extra term.
Mm-hmm. So it wasn't just purely conformal. There was always something extra.
It's not a mathematical statement.
Yes. It's a physics statement. So I guess the philosophy, which, so I'm repeating here, which arose from Witten's story and was developed by Segal and has been developed by other people, including you and Stefan Stultz, is that the way we should think of this, we should think of the field theories are, elliptic cohomology is some kind of invariant of field theories. So there's a variant of this where I have field theories which are equipped with an additional field which takes values in some manifold. And this goes to some target category. So here's the philosophy. Let's call these field theories on M. And there should be some function that goes to some kind of cohomology theory on M, which we'll call elliptic cohomology, because that's what it seems to be called. And sort of the best hope you could have is that, well, so this, if you think of this as an invariant of a manifold, isn't something you expect to be a homotopy invariant. Cohomology theories are homotopy invariant. So I think one conjecture, which is some very sort of vague version of one of yours and Stefan, is that elliptic cohomology is the homotopy invariant approximation to the construction that gives you all possible field theories on M. So that's a very vague statement, and you're not disagreeing, so that's at least roughly right. All right. But this is a story. A lot of progress has been made on this in the last 20-odd years. Somehow it always gets better, but this isn't a theorem as of yet. So the idea is that the Witten genus, so I'm not going to say this right, so maybe I should not say anything, but the Witten genus, it's a kind of push forward. It's a kind of integration that exists on this. One way to think about this, well, let me not try to go into this because it will take up time and will be useless. All right. All right, so that's sort of a rough story. What I want to do is I'm interested in the following things. First of all, I want to explain this using topology. So whether or not one can say, give a precise construction in terms of these field theories, we know that the Witten genus gives you a construction in topology, gives you a genus. In fact, it gives you a family's genus. So the topological instantiation of this is that one expects, and this is now a theorem, in fact, it has been a theorem for a while, which is that the Witten genus refines to a map of cohomology theory. In this case, the appropriate Borism theory is something called M string. This is the Borism associated to manifolds, which have this particular kind of data on their characteristic classes. And the target is some kind of elliptic cohomology. And the one we put in here is called topological modular forms. All right. So how am I doing on time? So what I want to do next is sort of change pace and think a little bit about the topology that's in question. So it turns out that in order to address any of these questions, it's not enough to think about ring spectra in the classical way that people thought about them in the 50s and 60s, but rather to use highly structured ring spectra. So I want to take a detour and say a little bit about highly structured ring spectra and some of their properties. So I think right now it's 5 minutes to 11, so let's take a break now, and I'll continue after the break. Yeah, that's fine. Oh.
About like this fiber of comparing units and the local.
Oh, that question. Okay, yeah.
I think I have now built some genera for TMS level structure.
Oh, okay.
So I'm writing that down.
Cool. Cool. That's awesome. All right. So.
The squeegee looks like a typical. I wonder how the how the Germans get.
Well, I mean, I'm sure practice helps.
Yeah.
So the first time I had to do this, I had never really. All right. Are we ready? All right. So, I've been talking about generalized cohomology theories. They're represented by spectra. Here's a spectrum. Maybe everybody knows what a spectrum is. I won't define a spectrum. Some cohomologies admit multiplications. If it's multiplicative, so it has like a cut product, then it's represented by something called a commutative ring spectrum. Now, spectra is a sort of a homotopy theoretic setting. So when I say I have a commutative ring spectrum, I mean I have a multiplication going from the tensor product of spectra, which is called smash product, which is, let's say, associative and commutative in the homotopy category of spectra. So it satisfies some commutative diagrams, or has some commutative diagrams which commute up to homotopy. But there's a refinement of this, which has been sort of one of the main advances of sort of the last n number of years in homotopy theory, which is that we can talk about structured ring spectra. So let's put that on this side. Structured commutative ring spectra. And there are various models for this thing, but they're all essentially equivalent. One model is called commutative S algebras, so I'll probably just use that language. But I'm not really dedicated to a particular model. So the proof of the theorem, or even the statement of the theorem that I alleged on the previous board about refining the Witten genus, relies on this notion of commutative S algebra. What I want to do right now is tell you what this buys for you for your cohomology theory. And the first thing it buys for you are something called power operations. So I want to give you just a very brief story about this. So the idea is that, let's say I have some cohomology theory, which comes from a commutative S algebra. Well, it's got a multiplication, a commutative multiplication. You have a cut product. Again, I'm going to be very vague about gradings. In fact, I'm actually going to be incorrect about gradings for the next section. So the idea is that, well, since it's a ring, I can take a cohomology class, little x, and take its, say, mth power. There's actually two ways to do this. there's an external nth power. Use an external version of the product, or the Kunith product. And then I can restrict along the diagonal embedding of x into the n-fold product. And this gives me the internal nth power. So cohomology is a ring in this case. And that's the nth power in the ring. The commutative S-algebra structure gives you a refinement of this structure. It tells you that this nth power map lifts to the following thing. I can take the nth product of x, my space, that has a natural action of the symmetric group, and I can form the Borel construction associated to that symmetric group action. And the commutative S-algebra structure, in particular, buys you this lift. I'll call this P sub m, and this is what I'll call the power operation. I can also restrict along the diagonal copy of x, which is fixed by the symmetric group. So that means I restrict, I land inside the cohomology of the product space x times E sigma m divided by sigma m. That's the classifying space. This vertical map, both vertical maps are restrictions to some base point. This is restriction to the base point in the classifying space. So both of these you should think of as a refinement of an nth power operation. So that's what the first thing that a structured commutative ring spectrum buys you a power operation. Here's the example. The first example of this was invented long before commutative S-algebras. In fact, this is really Steenrod's construction of the Steenrod squares. So in this case, the cohomology theory is mod 2 cohomology. Slot Z mod 2. The Steenrod squares are actually constructed from the symmetric group of order 2. And so Steenrod gives you a function from the mod 2 cohomology of x to the mod 2 cohomology of x times b sigma 2 with mod 2 coefficients. That's also B sigma 2 is also RP infinity. In any case, you know it's cohomology. This is the cohomology of x adjoining some power series variable, or polynomial variable, t. And so there's this function, p2. So this takes a class and gives me some polynomial in t with coefficients in the cohomology of x. The coefficients as functions of little x are the Steenrod operations. So I think it works out like this. So it's square n minus k of x times t to the k over k. The coefficients are the Steenrod squares. That's the usual indexing, which is actually inconvenient from this point of view. In particular, I'll notice one thing. I said here that if this construction refines sort of the naive power. In this case, if I take b sigma 2 and restrict to the base point, the class t is in dimension 1, goes to 0. If I restrict to the base point of b sigma 2, I lose all the terms with k positive. So I learn here that square n of x is actually the usual square of x. I should have said here, by the way, that this class is assumed to be in degree n. The way the indexing works for this is that you have to use a different formula for depending on what dimension you're in. Okay. So Steenrod's construction was actually this. This whole construction of power operations is just an elaboration of what Steenrod did in that case. I want to describe another example in more detail because it's sort of a motivating example in several ways. It's the example of Ktheory. It's a good example because you can sort of describe it more or less completely. It's very classical, and it sort of motivates things that I want to talk about for elliptic cohomology. So let's think about power operations in Ktheory. But I'm going to use a slightly different tactic here. I'm going to make use not of this Borel construction, which you can sort of name by saying it's some kind of Borel equivariant cohomology. I'm going to use honest equivariant K-theory. I think sometimes I'll talk like this. If I have a space with a G action, G is some, say, compact Lie group or even a finite group if you like, then I'll write K0 of X mod G. This is the equivariant K-theory of G with the action. So this is some kind of equivalence classes of equivariant complex vector bundles over X, formed in the way that K-theory is usually formed. Okay. So the construction of power operations that for equivariant K-theory, or for a general K-theory object, really goes back to Grothendieck. It's the theory of lambda rings. In fact, K-theory is an example of a theory that in some sense was invented in order to have power operations. K-theory, Grothendieck needed K-theory to prove some generalization of Riemann-Roch formulas, and in order he did that so he could say that K-theory was a lambda ring. And lambda rings are precisely the structure that comes out of power operations. The particular story I'm telling with equivariant K-theory was described by Atiyah. But even he somehow says that sort of the basic idea was sort of originated with Grothendieck's original construction. So here's the idea. It's a version of this story, only it's sort of much more sort of down to earth. So I'll take an element in K-theory. Well, that's an equivalence class of vector bundles, or maybe more precisely, formal differences of vector bundles. Let's suppose we have an actual vector bundle, just for X. Then the observation is that we can produce a bundle on the m-fold product of X by taking some kind of external tensor power. So this will live over the product. However, taking a tensor power is necessarily symmetric in permuting the variables. So even if I start with a class in the ordinary K-theory of X, what I get is an equivariant K-theory class. It's equivariant for the action of the symmetric group on the product. And this is a construction I'll call P sub m. This is the equivariant power operation. I can also do this, the analog of restricting along the diagonal. This is along the diagonal. In this case, the symmetric group acts trivially on the diagonal copy of X. And effectively, so this will now be sort of, if you like, the restriction to the diagonal. So it's just the ordinary internal tensor product. The symmetric group acts on the fibers. So one way to write this, that group is actually isomorphic to the usual K-theory of X tensor, the representation ring. A bundle which has sort of actions of a group on the fibers decomposes into bundles for various representation types. No, yes, they are. I don't know what else I left out. They're all M's. They should be. Okay. So for instance, let's call this P bar. So P bar of an honest vector bundle. It's not obvious here, by the way, this extends to the K group. I defined it for honest vector bundles. You have to show that it extends to virtual vector bundles. But if I apply this to an honest vector bundle, or even a virtual vector bundle, I can rewrite the output in here as a sum, let's say indexed by irreducible representations of the symmetric group. These are irreducible sigma m representations, complex in this case. So if I pull out the coefficients here, this gives me a bunch of functions from k of x back to itself. And these are all examples of power operations. So in particular, if pi is the sign representation, then this construction applied to an honest vector bundle gives you the mth exterior power. In this case, the operation on K-theory is usually called lowercase lambda m. So those are the lambda operations. So Ktheory, in particular, has functions on it called lambda m. They're not very, have complicated algebraic properties. So for instance, if you try to compute lambda m on a sum or a product, you get some complicated formula. But you can actually show that all the phi sub pi's can be written as polynomials in the lambdas. And you can encode all the algebraic structure that the lambdas satisfy, and you discover that k of x is a lambda ring. I'm not writing down the definition. So implicitly, it's a ring, commutative ring, with these functions which satisfy a bunch of properties. I want to describe briefly a different way of looking at this. I'm using the term lambda ring for what's sometimes called a special lambda ring. What used to be called a special lambda ring. Anybody who works with them now just calls them lambda rings. People who work a lot with them tend to just call them lambda rings now. All lambda rings should be special. Right. The special has to do with a particular identity, which tells you what happens when you compose lambda m with lambda n. That wasn't, I guess, in the original formulation. It was an add-on. But it's good to have that identity in there. Right. So let me give a different description of this theory, the setup. Oh dear. So let's take m equal to p. So I have this construction, the symmetric group, but let me actually restrict to the cyclic group of order p sitting inside the symmetric group. This is p bar of p. This is really k0 of x tensor the representation ring of the cyclic group. This is a restriction. So this takes an element in here and gives me some element in this ring. And it turns out it always has this form. It's something tensor the trivial representation plus, except I'll write minus, something tensor the regular representation. So the regular representation of the cyclic group is a sum of one-dimensional representations. And we can pick out the coefficients here. This coefficient is called psi p of x. This coefficient is called theta p of x. Okay. So this produces another class of operations. So I guess I told you they had to be some kind of polynomials in the lambdas, and they are. Well, I haven't told you which polynomials they are. Here are some properties these have. These can all be read off, but maybe I won't give the proofs. So if I can find them, it turns out one thing to do with this is to evaluate the cyclic group representations on characters. So for instance, I could evaluate representations at their character and evaluate that character at the generator of the cyclic group. That effectively takes the generating representation, which I called L, and replaces it with a pth root of unity. Of course, applied to expressions like this, the coefficients will go to integers. In fact, this thing just picks out the Adams operation. Sorry, that's what this thing is. And this thing evaluated at this character is just the Adams operation. Evaluating a character is a ring homomorphism. This is a ring homomorphism from this to C. And the part I'm interested in actually takes values in the integers. That's an artifact of the fact that this was actually really something that was invariant for the symmetric group, not merely the cyclic group. And we discover that psi p is a ring homomorphism. Oh, sorry. Back. I discovered this. Psi p is a ring homomorphism. But another thing I discover is if I evaluate at the trivial element, my character, then the analog of this sort of refinement happens, this thing turns out to be the pth power. And this gives me an identity that psi p of x minus p times theta p of x, because that's what happens if I plug in 1 for L here, that's actually the pth power. Usually I write this so that it's a formula for psi p. And one way to read this is that this psi p in particular satisfies a congruence. Psi p is congruent to x to the p mod p. Now, another thing you can show is you can show that psi p is a ring homomorphism. And I would be giving you the proof of that, only I'm running behind on time. Actually, more is true. Not only is psi p a ring homomorphism, this other operation, which actually determines psi p together with just the pth power, satisfies some identities, which I'll write down here. They're more complicated because it turns out psi p is not a ring homomorphism. Sorry, I call it psi p. It's theta p is not a ring homomorphism. I'll write them out. Oh, if I can find them. They look complicated. But what those formulas are the formulas you get if you know that psi p is a ring homomorphism and this identity is true, and you figure out what you go and try to figure out what identities theta p should satisfy, and would necessarily satisfy if you can always divide by p. So in a torsion-free ring with all these operations, the fact that this is a ring homomorphism implies these identities. This structure, R, together with theta p satisfying these identities, is what's called a theta p ring, at least to topologists. It's also called other things to other people. In particular, what you're doing is I have a commutative ring, like Ktheory. I have some endomorphism of that ring, psi p. It's a ring endomorphism, which lifts the Frobenius, the pth power map. It's a lift of Frobenius. But it comes with a little bit more, which is this theta. We think of this theta as a kind of witness for this congruence. It's not merely the congruence is satisfied, but we have a particular thing to stick in this formula. And it's natural. It's a natural operation. So here's an observation about lambda rings, which is basically due to André Joyal, which is that a lambda ring is basically a bunch of theta p rings glued together. So, theorem. So, a lambda ring, so I'm actually writing the equivalence of categories, that's the same as a commutative ring R together with theta p ring structures for all primes. These are theta p ring structures, which are compatible with each other. You can write it like this: theta p psi. I don't know if I have an upper or a lower, it doesn't matter. Theta p psi q is psi q theta p for all primes p and q. In particular, if R, there's a corollary, which is actually an earlier theorem of Wilkerson, which says that a torsion-free lambda ring is a ring, commutative ring, with compatible lifts of Frobenius. For all primes p. Compatible means they commute. Psi p, psi q, equals psi q, psi p. If you're torsion free, then giving the theta p, it's uniquely determined once you know the appropriate congruence is satisfied. Okay. So this is sort of a very different description of what a lambda ring is. It's entirely in terms of phenomena which exist at primes. So I guess I want to say two things about it, very briefly. One thing is that, all right, let me say, well, let me make this very brief. Actually, maybe I won't say anything at all. I'll just observe that this is some structure associated to K-theory. One thing I should say is I should point out the switch I performed. I started out talking about commutative S-algebras, and I said those had power operations. And then all of a sudden, when I went to K-theory, all of a sudden I got equivariant. I didn't have to do that, but doing that actually had benefits. So the earlier story would have suggested that maybe K-theory is some kind of commutative S-algebra, and therefore I should have power operations like this. So K-theory is a commutative S-algebra. But there's more structure in K-theory. In fact, we can refine the operations which come from a commutative S-algebra, which K-theory does have, to equivariant operations. So I described a refinement here. These operations were constructed by Atiyah in the 60s, I guess. But only, I guess, recently do we have sort of a good homotopy theoretic framework for saying where these operations live, or more precisely, what structure on a spectrum gives you these kinds of operations. And this comes from the fact that K-theory is a global intercommutative ring spectrum. Commutative. I should probably modify global. It's globally equivariant. So K-theory has equivariant versions, and it has them for all groups, and they're somehow compatible. But then there's also some kind of very enhanced version of multiplicativity, which gives me this enhanced power operation. And that's the one that I wrote down. A question that is a question at the forefront of my mind is, how do you do this sort of thing for elliptic cohomology? So I'm going to state some theorems which tell you about elliptic cohomology having something to do with commutative S-algebras. And I think it's an open question still to what extent we can refine that structure to something that's globally ultracommutative. So that's lurking behind everything I'm going to talk about, although I may not address that specifically. Yeah, well, in the analogy, I didn't put next to the m here, so I won't put next to the m here. So that's the trivial action. The symmetric group's acting trivial on that x. I could have put the Borel construction for x to the m here, in which case I would have put x to the m over sigma m here, but I didn't write it that way. Yep. So that's a very good question. This theory actually, if you try to produce the psi p for this, you actually only get an operation that takes values in p-adic K-theory. Even if you start with integral K-theory, the power operation construction only gives you a p-adic version of the Adams operation. That's just the way that works. So you need something more to produce an integral version. It involves some kind of representation theory or something, whether or not you use ultracommutative spectra. It uses something more than just the fact that K-theory is a commutative S-algebra. Does that answer the question? All right. The structure I'm calling a lambda ring is, well, the one that involves having little lambdas. It's the one that will actually live on this theory a priori. Turns out this theory also has it, but you cannot read it off from this notion of power operation. You need the equivariance to do it. All right. Notice I'm talking faster. Can you imagine why that is? All right. Let me briefly return to elliptic cohomology and sort of give some very brief outline of the current state of the subject. And then I'll close with some idea of where I'm going. So to cut the story short, we have a beautiful theory of elliptic cohomology for many contexts. And it's described in terms of a moduli stack, in terms of commutative S algebras. Great. So I should probably say something about something called elliptic spectra. So this is a first sort of a first definition of what an elliptic cohomology theory is. I could just declare some theories to be elliptic cohomology theories, but it's good to have a reason why they deserve that name. So an elliptic spectrum, it's an even periodic homotopy commutative ring spectrum. E, together with, let's write this as data, E, C, and alpha, together with an elliptic curve, an algebraic elliptic curve, C over spec of pi 0 V, that's a ring, together with an isomorphism, alpha, from the formal group of E to the formal completion of the elliptic curve at the identity element. So I've thrown in a bunch of things here. An even periodic cohomology theory, it's a multiplicative cohomology theory. It's even in periodic. Periodic means that pi 2 of E is an invertible pi 0 of E module. Or actually, more precisely, it means that pi 2 of E tensor pi minus 2 of E over pi 0 of E is actually pi 0 of E. For instance, K theory is periodic because it actually has a periodicity element in dimension 2. So that has the pi 2 as a basis, as a pi module for pi 0. Even means that it has no odd homotopy. Such spectra are automatically complex orientable. This means that, in particular, if you take the cohomology of BU1, also called CP infinity, that is a formal group. The way I'm going to write this, I'm going to write this in geometric language. This is a one-dimensional commutative formal group law. Okay. What that means is really that the E cohomology of BU1 is a power series ring on one variable. And the geometric interpretation of that is as the formal affine line. And then the fact that U1 has a multiplication, which is also a group homomorphism, means that this thing, the ring E0 BU1, is some kind of Hopf algebra.
If you said pi 2 is convertible and not free, then don't you get a formal group in that?
Yeah, so this, what I'm telling you, is precisely what happens if pi 2 of E is actually a free module. If it's just a locally free module, then this isn't quite right. I can still talk about this. But, and I can even say it's a one-dimensional formal group, if I set up my definitions appropriately. But if you like to write things in terms of a formal group law, you have to choose a power series generator of this ring. That happens in most familiar examples, but it's actually not part of the definition. Okay. Okay. So this is a formal group. It's a geometric object that is sort of, it's the formal completion of a one-dimensional Lie group or something. Well, an elliptic curve is an algebraic curve that's a group, an abelian group. And so we can take its formal completion at the identity section. You should think of this as a family of elliptic curves over some scheme, which is pi 0 V, and I'm taking the completion at the identity section. So we're going to attach to our cohomology theory an elliptic curve whose completion is identified with the formal group, which is associated to E. This is the thing I'm calling GE. Okay. So this is the notion of an elliptic spectrum, and any such gadget in particular gives you an elliptic cohomology theory. So for instance, there's a large class of such theories, and I can describe them using the elliptic moduli stack. So here's a fact. So for any flat morphism from spec A to the stack of elliptic curves, there exists an elliptic spectrum. The moduli stack of elliptic curves, whatever that is the thing that classifies families of elliptic curves. So if I give myself a map to the elliptic moduli stack, that's really corresponds to giving an elliptic curve over spec A. And the fact is that if that morphism has some condition, in this case flat, then I get an elliptic spectrum, which I might call ELL of C. It comes with an E, and it comes with an elliptic curve, which is the given one, and some alpha. And for people who know these things, this is some manifestation of what's called the LANtheory exact functor theorem. So it's actually a kind of algebraic construction of a cohomology theory from some algebra geometric data. So there are many elliptic spectra from this construction, including some of the earliest examples like the LANtheory-Raphael-Stong elliptic cohomology. However, this isn't good enough for dealing with these kinds of questions that I want to talk about. Notice that those were homotopy commutative rings. They weren't structured. They weren't commutative S algebras. So let's state the theorem. So this is the theorem of, I guess, Gorse, Hopkins, and Miller, although maybe with some modifications or additions. The observation is that if you look at a more restrictive class of families of elliptic curves, you can actually obtain cohomology theories which are given by commutative S algebras. In fact, here it is. So Gorse, Hopkins, Miller, and the way they say it is this: there exists a sheaf of commutative S algebras, which is usually called O top, on the moduli stack of elliptic curves, such that in the étale site, let's actually say, let's put that in the étale site, such that the associated cohomology theories associated to étale morphisms, to the stack of elliptic curves, are actually elliptic spectra. So such that, write this out properly, such that for each étale, whatever that means, spec A to M ELL, classifying some curve, the associated ring spectrum, which is O top of C, that's a commutative S algebra, comes with the structure of an elliptic spectrum associated to the elliptic curve C. So the curve, so that it's paired with the elliptic curve C. So, all right. This has elaborations. Notice we had to restrict the kinds of maps we have. This condition about being étale, well, I didn't explain what it was, and I'm not going to today. But it's a kind of a condition about deformation theory. You can actually restate this entirely in terms as a condition about the elliptic curve itself. It says that it's essentially its own universal deformation, at least infinitesimally. All right. There's an extension. This can be extended to a sheaf, which I'll still call O top, but a sheaf on the compactification of the elliptic moduli stack. That's called MELL bar. I think originally they did this in the étale site, but it can actually be done in something called the log étale site. I'm never really going to talk about this in particular, but this extension is important. It's due to Lawson and Hill. Right. A consequence of this is that you can form global sections. So, for instance, the global sections over the elliptic moduli stack of O top is what's called TMF with capital letters. And this refinement that lives over the compactification is called TMF with only some capital letters. This is a terrible convention, but we're stuck with it, it seems. There's a further object, which is called TMF with no capital letters, and that's kind of defined in a really stupid way. It's the -1 connected cover. Okay, I'm running low on time. Probably you may have seen talks about these sort of objects before. This is a periodic theory. Each of these objects have associated to them a spectral sequence that computes their homotopy groups. Let me write it for this one. There's a spectral sequence that computes the homotopy groups of capital T, little m, little f, and it comes from the cohomology of the moduli stack compactified with coefficients in tensor powers of the bundle omega that I introduced earlier. So there's a spectral sequence. These spectral sequences do not generally collapse at E2, although they're not too far off. If you invert some primes, if you invert 6, actually, which is 2 and 3, then this actually does collapse at E2. It gives you homotopy groups in all degrees, because H0 is the ring of modular forms. The moduli stack of elliptic curves is basically a one-dimensional object, and because it's compactified, it's sort of a proper one-dimensional object, so it has a kind of Serre duality. So there's another contribution by H upper 1, which turns out to contribute negative homotopy groups. If I don't invert 2 and 3, then I have some torsion as well. So people take a connective cover of this, and they call that little TMF. This does not have such a good modular interpretation. Okay. There's an extension of this by Lurie. Let's see if I can fit it here. Lurie. So Lurie says we take MELL, let's just do the smooth one, with its structure sheaf, and he gives an interpretation of this. This is the moduli stack of derived oriented elliptic curves. What's a derived oriented elliptic curve? Aha. It's a derived elliptic curve with an orientation. I'm not going to tell you anything about derived algebraic geometry for the reason that I know nothing about derived algebraic geometry. Well, nothing in particular that is useful to you. Let me say a little bit. I will talk a little bit, I think, in a later talk about what this word orientation means. It's actually an interesting one. So we can at least say something about this definition. I defined on a board, it's a little bit gone now, the notion of an elliptic spectrum. So there's a notion of a derived elliptic curve. Here, the idea is that A is not a ring. A is a commutative S algebra. And E is not a usual elliptic curve, but it's an object in derived algebraic geometry. It's some space or some topos or something equipped with a structure sheaf, which is given by commutative S algebras. And it has some underlying classical scheme that is an elliptic curve. So it's a derived group scheme, abelian group scheme, whose underlying classical object has the underlying classical elliptic curve. That will have to do for a definition. An orientation is the analog of the alpha I put down before. It's I have this E. It has some kind of formal completion at the identity section. On the other hand, we have an analog of a formal group. Remember, A is a spectrum. It's a commutative S algebra. I can look at the function ring from BU1 plus into A. That's a commutative S algebra in its own right. It's in some sense the cochains, the A-valued cochains on A. And the extra data of an orientation is an isomorphism between these geometric objects. Okay. And so that is the data that is classified by this object. The thing I wanted to point out is that something comes out of this, which is that associated to Lurie's construction, his derived stack, are equivariant elliptic cohomology theories. So as a consequence, for each, let's make a somewhat explicit statement, for each spec A to MELL O top, which is a tall, there exist equivariant elliptic cohomology theories for all compact Lie groups. Equivariant elliptic cohomologies for all compact Lie groups G. Let's call these, I don't know, A sub G. In particular, these theories want to take values in sheaves on an algebra geometric object. So I'll just give it one particular case. In particular, the U1 equivariant theory is a theory on spaces with a U1 action, and that takes values in quasi-coherent sheaves on what I'll call script C, the curve classified by this. Remember, this is a derived elliptic curve.
Can you say something about derived completion?
No. I mean, what should I say about it? I'm not going to define it. I'm in no position to define this at this point. So this object, maybe I should call it C here. I guess I called this one E and this one C. That's awkward. Doesn't matter. This one has a section, identity section. That's part of the structure of being an elliptic curve. It has a structure sheaf. So you have to form some kind of completion. There's an ideal sheaf there if you take homotopy groups. So you have to turn that into a homotopical construction to give the completion of it as an object. The tricky thing here is that it's not just enough to have an isomorphism schemes here. This is a group, the elliptic curve. This is a group object. This is also a group object, some kind of formal group. You have to even say that in order to say what it means to have an isomorphism here. So that's a fairly sort of complicated thing to talk about. Let's see, I have how many minutes? N minutes left? All right. So one thing I hope to talk about. So let me say a little bit about what's going to come next. All right. So there was more here that was going to be in this talk, which is going to be in the next talk, because I'm running out of time. One thing I want to talk about is the theorem. So I'll talk about aspects of this theorem. And this theorem has precursors to Ando, Hopkins, and Strickland. In fact, I'll talk about that more, I suspect. This produces a map of commutative S algebras from M string to TMF. TMF being this thing up here. Maybe it's gone now. Oh, it's still there. Right. The interest of this is that to understand what's going on here, we need to produce a map of commutative S algebras, which means we have to confront power operations. And so, in fact, Ando, Hopkins, and Strickland developed a theory of power operations for a very special form of elliptic cohomology, which we can more or less identify with Morava E theory at height 2, in order to solve this problem. So I'm going to tell you aspects of that story. And it's actually a very beautiful avatar of what I think should happen generally. And I'll also, however, also talk a little bit about some aspects of our proof, which doesn't use power operations as obviously, but in fact they're still in the background, and has some interesting connections to Heck operators. So that's going to be one part of these talks. Another part of these talks will be an attempt to say something useful about what power operations should be for equivariant elliptic cohomology. So I actually sort of made a little story where I said, well, Ktheory has these equivariant power operations, and we understand that has to do with some kind of ultracommutative global ring spectrum, whatever that is. This story, of course, Hopkins and Miller and its extensions and the extension by Lurie, well, that ends up producing equivariant cohomology theories, but there's no ultracommutative ring spectrum in sight. So an important question is, what do you need to put in to produce that theory? And so that's going to be the other aspect of these talks. What shall I close with? So I think the right thing to do is to stop here. And so what I'll do next, I'll tell you what I'll do next time. I'm going to tell you a proposal for what power operations in equivariant elliptic cohomology ought to look like based on analogy with the story I told you for Ktheory. So that's a statement that you can make, whether it's true or false. But it turns out there are several different cases where we can actually produce those operations. One is Morava E-theory, one is elliptic cohomology associated to the Tate curve, and one is Gronowski equivariant elliptic cohomology, which is an complex analytic valued elliptic cohomology. All of those admit some form of power operations which have this desiderata which I'll tell you about. So first I'll tell you about that desiderata and make a proposal, and then I'll focus on the case of Morava E-theory, which is probably the best understood. So that's the plan for the next talk. Thank you.
Well, thanks a lot for the first talk. So do we have some questions? So the equivariant theories you get from Lewis' work, do they really come from the Wheeling complexity groups by some right-use process, or is there?
Well, it's complicated.
This question
Yeah.
I have a chance?
So that my understanding is that they come from Wheeling groups by a right-induced process. So you have to be careful about how you carry out that induction. I'm of course perfectly happy just to have a theory for abelian groups.
That's really where the information and the work lies.
That's sort of where the interest is, and because of this induction, that's sort of the key case anyway.
What's the kind of structure I need to write this thing down? So A is some commutative ring spectrum.
A is some commutative ring spectrum.
What is this map to? What kind of
What's E?
data give you?
Which thing are you pointing at here?
And this, to get the equivariant cohomology.
That's actually a very good question. It's really hard to figure out how to build a map from spec A to MELL, O top. Despite the fact that, so Leary's theorem is a nice package. It tells you that some things that you want are equivalent to these maps. But that leaves you the problem of computing these maps. And that's really a problem of computing. It reduces to a problem of computing maps between commutative S algebras, which is often difficult. So in fact, I meant to say this, sort of the one case that you know is actually built into the statement of the theorem. Remember I talked about the étale site. It turns out that one class of maps that you know you can construct are associated to classical étale maps to the moduli stack. So that was the original Gorse-Hopkins-Miller formulation in terms of the étale site of the classical moduli stack. And that, so in the new formulation, you still have those maps. You know those exist. You can actually, if you like, it's a full subcategory of the category of derived elliptic curves, which is a very complicated category. But there's a full subcategory that's equivalent to the category of étale maps to the elliptic moduli stack. So there's this core that we can really understand. And that's produced by the theory. It's the same thing that's produced by the Gorse-Hopkins-Miller theory. If you want to extract out different elliptic cohomology theories, it's much harder. In fact, that's a really important problem, which I meant to mention, but I dropped it. To figure out something about what other kinds of elliptic cohomology theories you can construct other than the examples given by étale maps or the examples given by the universal curve, which Leary's theory also tells you you have. That's the other class of examples that sort of exist for free. And there's also one more question, which is that there are actually many elliptic cohomology theories that aren't represented or aren't known to be represented by commutative S algebras, including interesting ones. And so although this is a beautiful theory, it says nothing about elliptic cohomologies that aren't represented by commutative S algebras, but perhaps are represented by structured ring spectra that aren't commutative but have EN multiplications. And that's sort of completely open. For instance, I've gotten interested in, there's a version of elliptic cohomology associated to quasi-modular forms. And you can actually say what the spectrum is, but I don't know what kind of, I know it's strictly associative, but I don't know what more it has than that. It's a sort of question that I don't really know how to answer. And there are lots of questions like that. So despite the fact we have this beautiful theorem, there's actually lots of open stuff to work on here outside of the setting where I'm going to talk about.